Hello, everyone. I'm Owen O'Malley. I'm a co-founder and architect at Hortonworks, and we're here today to talk about a file format benchmark that we did and compare off Avro, JSON, ORC, and Parquet. Who am I? I've been working on Hadoop since the very beginning, back in January of 2006. Obviously, Doug Cutting and Mike Carafello were working on it before then, but I worked on it before it became Hadoop. I've worked on MapReduce, some on HDFS as architect for security, and more recently I've been working on Hive and ORC. And along the way, part of working on this stuff for 10 years is I've touched a lot of different pieces. So for example, I've done a lot of the work on sequence file. I did a little bit on RC file. I did a lot of the work on ORC, and I've actually even worked on a file format called T-file. Anyone actually heard of T-file? Wow, all the yahoos, not surprising. It's actually in Hadoop. Not very many people use it, but it is there. And I actually was in some of the design meetings for Avro. So I've been working on this stuff for a long time. Actually, one of the interesting historical notes about that design meeting with Avro, Christoph, one of the co-founders of Cloudera, was there. And at that point, he was working at Google. And I said, you know, it'd be really great if we had protobuf. And that was actually part of the reason he made a call, got Google to open source protobuf. So that's why we actually have protobuf in the open source. Okay, so what was the goal? The goal was really as a science experiment. We needed to figure out what unknowns there were and figure out how we could make the different file formats better. I had been to a couple presentations comparing them, and I was never happy with any of the analysis because they were either too small, they used private data, which heaven knows I understand the benefit. If you've got commercial data, it's really nice to use that data, but then you can't share it. And part of what's important with benchmarks is actually having them open source so they can get reviewed. When I was in university, the first time I got access to the Unix source code, I was like, oh, this is wonderful. Now you can actually open up the covers and see how everything works. And so that's hugely important. You need to be able to look inside the hood, see what works, how it works, what the use cases it was designed for are, and what it's doing. So that's really important. I wanted to use some real and diverse data sets. We all love TPCDS. We've used it perhaps too much, but just like a person who exercises using the same exercise over and over, our arms are getting really strong because that's what TPCS tests, but it's one particular kind of test. We aren't testing other kinds of data sets, we aren't testing other kinds of queries. And so I really wanted to go out, find some of the publicly available data sets and do some benchmark based on those, and make sure that everything was open and available. Okay. So the file formats. I'm going to cover a little bit of background on them just so that everyone knows what they are. Avro came into existence when the primary format that we used in Hadoop was called sequence file. Okay, does anyone still use sequence file? Oh, good, a few of you. Sequence file had this very efficient protocol. It's still incredibly efficient, called writable. But the bad side was that sequence file was just a container. It knew nothing about the contents. And furthermore, everything was defined by the programmer so that it didn't have any context about what was what, except that there was this thing called a key and this thing called a value, and those were Java types. But because there was no description of what was in those fields, other than the Java type that implemented it, that meant that you couldn't do any kind of analysis. You couldn't look inside. Everything was just a black box. And So you were extremely limited in terms of what you could do. What was even worse was that in order to do schema evolution, right, if one day you had 100 fields, and then your business comes and says, oh, I need you to add these 5 more fields, now the user had to deal with that upgrade, right? They had to deal with the schema evolution because it was all being managed in user code. Now, sometimes the user did it right and was planning ahead, but a lot of time they didn't, and so they got into trouble. So that's really the use case that Avro was set up to make, and it does that quite well. The schema was completely segregated from the data. That is very different from protobuf and thrift, for example, where the data for protobuf and thrift, you have some of it with the data and some of it separate. With Avro, everything is separate. Without the schema, you can't understand what this data is at all. You just have bytes and no way to parse it. Finally, it's a row major format, which means that each of the fields in the row is stored right next to each other. That has a lot of advantages if you're reading the whole row, but it's really unfortunate in a lot of cases where you just want to read part of a row. The next format that I wanted to include was JSON. We still have a lot of users coming in with JSON documents. It's a text format. There's a huge numbers of parsers. I don't think there's any language in the world that is used to program computers that doesn't have a JSON parser, and several usually. The schema is completely integrated with the data. You have no idea what type it is until you've read the whole record, and actually the whole set of records. It also stores the row together, and its compression is always applied on top. Now with Hadoop, applying the compression on top has a lot of problems, because one of the things that distributed computing likes to do is split work for a particular file into 2 pieces. And that gets really hard with compressed files. So if you have an uncompressed JSON document, you can split that into multiple pieces and assign each piece. But if you want to gzip it, then that doesn't work anymore, and it won't let you split it. All right, so ORC. ORC stands for Optimized RC File, and it really started because we were working on the Stinger project in Hive to make Hive faster. We wanted to go through and put a vectorization engine in and let Hive use the vectorization where each operator processed 1,000 rows at a time. Doing 1,000 rows at a time lets you use the CPU a lot more efficiently and lets you avoid a lot of operator pipelines. Before we did that, each operator in the Hive stack, so if you were adding one and then multiplying by something, each operator was a separate method call, and in reality it was like 40 different function calls for each value. So it obviously ran very slowly. We wanted to go to vectorization. We needed a better format, and so that's was where ORC came from. The schema is also completely segregated into the footer, but now it's a column major format, so that column 1 is stored separately from column 2, which is stored separately from column 3. They're still in the same file, but they're separate ranges of bytes. It's got a rich type model. We copied exactly the type model from Hive so that you have all the same types. And it's got integrated compression, indexes, and stats. So that means that for every column, you have the type for the whole file, but you also have the minimum and maximum value for each column. You have how many items are in there, and then you have that same information propagated down in a 3-level index. So you have it for the whole file, each stripe, and then each set of 10,000 rows. That lets you do a lot of fun things that we'll talk about later. All right, while we were busily designing ORC, Twitter and Cloudera did Parquet. Parquet was originally designed for Impala and for Pig, amusingly enough. They also have a lot of the same characteristics as ORC, but they have a simpler type model, which has some good sides and some bad sides. It means that their reader and writer has fewer types that they have to worry about. But on the downside, that means that they can't have as detailed encoding. Because ORC knows that a timestamp is actually a timestamp, it can treat it like a timestamp. It knows, okay, most timestamps are going to be around 2015. So it chose the base time as 2015. Parquet, on the other hand, said, oh, it's just a big long integer that's down to nanoseconds from 1970. That means that they do a lot less well at encoding that. But they've also added integrated compression and indexes. Now, one of the other major differences is that Parquet was based on Google's Dremel paper. Now, we read the Dremel paper, but we were like, okay, that's really complicated. It'll make the implementation very complex. So when ORC has, for example, a list, it encodes the number of elements in the list for each instance of the list. So if you have 4 instances followed by 3 instances followed by 5 instances, you'll actually have a 3, a 4, and a 5 in the data for those intermediate columns. Parquet pushes all of that down to the bottom. And then they have to build a DFA to reconstruct it based on which columns they're actually reading. So they've got a lot of complexity down there. And amusingly, there's actually some things they can't represent. Like if you have a list in Parquet, you can't actually put nulls in that bottom list because there's nothing to push the fact that there's a null there into. And so it'll just disappear. Okay, so data sets. The first data set I found based on that link, and all of the taxi rides in New York City get encoded into this database and then released for free. That's an amazingly interesting data set. Actually, that link has not just the link to the data, but has some really nice analysis of what people were doing. So it's a very simple table. It's got 18 columns with no null values. And they're pretty simple types. It's doubles, integers, decimals, and some strings. Now, the decimals, that was obviously a choice. I could have chosen to encode that data using integers for cents because those are for the money, right? It's got broken out pieces of how much the fare was, how much the tip was, how much the tolls were, all that. So most business users like to use decimals for that. Never ever use floats. If I catch any of you guys using floats for that kind of money stuff, I'm going to slap your hands really hard. Actually, I did have a customer use doubles once, and I got to explain to them why when they added it up different ways, they got different answers. That is actually a design characteristic of floats and doubles, which is why you don't want to use them for money. Please never, ever use doubles for money. But anyway, so I used decimal for there. You could use integers or longs and just say it's pennies instead of dollars, but I thought it was a more accurate representation to use decimal. This actually is from that paper. The one on the left is a dot for every pickup from the taxi cabs, and the one on the right is a dot for every drop-off. And so you can see that it covers the whole area. Actually, if you look close, you can see Central Park and the airports. Okay, so another data set that's very, very different is the GitHub logs. The GitHub logs basically correspond to every time a user on GitHub does something to a public repo. And so that has a very large schema. It's got 704 columns and pretty much every type in the kitchen sink in that data set. It's very, very nested and has a lot of nulls. One of the characteristics of this is this is pretty much the use case that Dremel was, which was the basis for Parquet, was made for, was analyzing logs and log data like this. And the benchmarks, I tend to use half a month of data, which is 10.5 million rows. Even that's a big chunk of data. Now, GitHub publishes this data for free, which is awesome. Google hosts it, which is even nicer. But it's just this big pile of JSON documents. That's awesome, but they didn't give us a schema. I'm like, okay, that's great. So one of the first action items was to write a tool that, given a pile of JSON documents, will go through and make a Hive schema for that pile of JSON documents. So that actually is open source too. And it basically goes through each record and figures out for each of the fields in the type, including all the recursive fields, what type it has to be. And it's making guesses. It's based on heuristics. If it looks like a date, it'll say it's a date. If it looks like a string, and it'll say it's a string. Now, if a string and a date are next to each other, it'll say, oh, the date must have been a red herring. It must have been a string. And so it promotes like that. The schema for the GitHub archive is huge. It's 12K. So yeah, just picture 80 columns, really long. No way you would have come up with that by hand. Okay, now finally, one of my favorite customers they use Hive a lot, and they have a table, but of course, as always, you're not allowed to use a real customer's data in open settings. And so they had a test framework for generating data, and I copied a lot of that. So it's their schema, but with generated data. So this has 55 columns, a little bit of structure, not that much, and lots of timestamps, longs, strings, booleans. They should actually have decimals, but they've changed them all to longs because they... Actually, that's one of the challenges with Hive, is Hive decimal doesn't work very fast, and so this customer actually, they know this, and so they have been using longs instead of decimals, and actually instead of even cents, they use millions of a cent. And this, you can choose how much data to generate, and so I've been using 25 million rows. All right, so storage costs. Data size matters. When we first went to Facebook to talk about ORC, they were really excited because they've got so much data that they care immensely about how tightly they can pack it. And as a matter of fact, they wrote a blog post that saying it after they'd finished, by the time they'd replaced RC file with ORC, they had saved 1,400 computers worth of data. So that means that they could get rid of 1,400 servers that they didn't need anymore. So with Hadoop, it's great. You can store everything you need. You can throw more stuff in there. But it's nice when you can use less of it. ORC and Parquet use run length encoding and data dictionaries. Run length encoding is basically based on the observation that almost all data that you get from real data sources comes in runs. Not as much as TP-CDS. One of my favorite data sets is the TP-CDS, like I said, because they've got some of the tables where they've got these really nice, every 10 rows is like a batch. It compresses really well, but no. Real data, you still get a lot of very important values compressed using run length encoding and dictionaries. So that encoding can't be turned off because it executes really quickly. Dictionaries are the same thing. You often have a relatively small set of values for a string column, and so the dictionary encoding will keep one copy of each of the strings and then reference into that dictionary. All the formats have zlib, gzip, which gives you tight compression but is slower, and snappy, which gives you a little bit of compression but is much faster. So with that said, This is why you don't want to use JSON. See that bar on the right? That's JSON. Actually, can you guys even read the? So the far right is JSON with no compression, and then JSON with snappy is next to it. And then Parquet and ORC with zlib are on the left. So this kind of matches what you'd expect to see, where JSON with its schema embedded in each string, you end up with lots and lots of duplication. All right, so the first data point is don't use JSON, please, don't use JSON. You almost always want to use snappy or zlib compression. One of the features of Avro is to make it splittable. They go 15K and then put a synchronization marker, 15K and then another synchronization marker. That works great for splitting the file into pieces. It unfortunately really screws with your gzip because now your window for gzip is only that 15K. So you end up with not as good a compression as you could get with better windows, longer windows. The Parquet with zlib is a little bit smaller than ORC, although if you look at the charts, it's not huge. But I wanted to do a little bit of a deep dive on what was going on there. So I grouped the columns by type. And because they're columnar, you can actually look at the different sizes. So this is a map of the different columns for that taxi data set, grouped by what type they are. And so when the green line is higher, that means the ORC is bigger, and when the orange line is higher, that means that the Parquet is bigger. So as one of the people who cares about fixing these things, what that says to me is that the Parquet is doing a much better job of compressing the doubles, right? Because the ORC one is always higher through this section that's all doubles. But on the other hand, you can see that my point earlier was correct, where timestamp always goes the reverse, right? Timestamp is much smaller in ORC than it is in Parquet. So this is one of the things that we were trying to learn is what works. Okay, now when you look at the chart for sales, now you can see that the JSON is still huge, and the ORC and the Parquet and the Avro do much better. Now, one of the interesting cases in this, because of the particular details of this schema, actually the ORC does extremely well. Even without gzip, it does, or snappy, it compresses really tightly. So yeah, it was a pleasant surprise, but the things that feed into it, the string columns have a lot of small cardinalities, so the dictionary encoding does really well. There's a lot of timestamp columns, and there are no doubles. See, the happy case. Although, one of the reasons it hasn't come up more is because, yeah, doubles shouldn't be used in financial applications. Now, one of the points that needs to be stressed is that, of course, this is a synthetic data set. So we need to go back and take these tools and apply it back on the customer's real data to see what things we can learn with the real data. The data generator also should get some non-smooth distributions, because right now everything's a smooth. Okay, now the GitHub data set. Again, the JSON is the big stuff. Avro is also pretty big. But here on the other side, you'll see some interesting things. In particular, Avro is also the smallest once you throw gzip on here. That had me scratching my head for a while. I was like, what in the frick is going on there? And it turns out that what's going on is that it goes from the worst when it's uncompressed to the best when it's compressed. And after looking at the data, you can start to see why. There's lots of repeated strings and string fragments between the different columns. ORC and Parquet only do compression within a column because they're storing each column so that you can decompress it individually. That's great, but it means that you don't learn the fact that HTTPS is a really common substring until you learn it in each different column. And so Avro actually compressed much better because that commonality mapped out. Now, so what do we do about that from the ORC and the Parquet side? I think we're going to look at getting shared dictionaries across, at least for fragments, at least having some common fragments so that the web properties, so people who are dumping logs into can get HTTPS encoded as something smaller than 6 characters. But it'll definitely be one of those to go through. And again, this is science. When you learn things in science is when you hit something that completely surprises you. And I was completely surprised when we got these results and Avro was compressing tightest of everyone. All right, so use cases. So the standard base case is always going to be, what if I just need to read all the data? And all the formats except for JSON are splittable. Actually, even JSON is splittable as long as you don't care about compression. So I took my big data set or my big 3 data sets and basically ran them on a Linux computer and using the Java micro benchmark handler generated these. Actually, JMH is a really nice tool. It does a nice job of running multiple iterations and storing the results. So this is the number of microseconds per record that each of the formats used. So you can see on the tall side, there's JSON with using the most time. So yeah, don't use JSON. Okay, I should just change the title to don't use JSON. And the other ones are all pretty similar. They vary a little bit in the details. Those details may matter some, but in the overall scheme, it probably won't matter that much. And again, part of why JSON is slow to read is the same reason it's slow to write, is because the JSON parser has to parse those strings over and over again for each row. And it needs a lot of string parsing. All the other formats are binary, and so they aren't parsing strings. Now, JSON is obviously convenient for putting it in there, but parsing it is problematic. All right. Now, the other ones, if you look, there's an interesting trade-off. Went the wrong way. Sorry. So the fastest one is ORC with no compression at all, followed by none, or Avro with none, and then Snappy with ORC. So what's going on there is that the compression actually costs you time. So it's winning you time and costing you time at the same time, because in order to read it, you have to decompress, but at the same time, you get to read less data. So that's one of those cases where you really need to try it to see what the right trade-off is. In this case, you can see that the overall wins weren't that much. So you might as well get the smaller size. Okay, this is the sales data. One of the interesting things here is that, again, it grouped almost precisely by file format with minor variance between which compression one it used. So the tighter compression didn't help as much as you would have thought, but ORC, having a small file, did well, and then Avro did next, and then Parquet. Now, one of the things that the benchmark also gathers is how much time the garbage collector spent going. And that actually started to become a factor in this one. Avro had almost no time spent in the garbage collector, which surprised me. But ORC had a little bit, and then Parquet had noticeably more. And so that probably explains at least a portion of that performance difference. Now, one of the differences between Parquet and ORC is when Hive put in the vectorization API, Parquet implemented it so that everything upstream of the reader could be vectorized. But the way they did it is by reading into objects and then taking those objects and stuffing them into the vectorized batch. So that works. It's efficient. Heaven knows I played that same trick when I did ACID for Hive. But they really should go back and make a reader that goes straight into the vectorized row batches directly, because that'll get rid of a lot of that garbage collection. All right, now the GitHub. Again, notice these values are much bigger. Parquet is really being slow. It even passes up JSON, and then Avro and ORC are underneath. Obviously, my slides will be on the... And here, garbage collection became even more critical. And so ORC is doing 2 to 3.5%. Avro is minuscule, and Parquet is spending over 10% of its time in the garbage collector. So that definitely gives us places to look for improving Parquet. Now, one of the things I noticed is that these tables with a lot of columns are getting divided up because I use the default values for everything. So they probably should have had bigger stripe sizes. I didn't get a chance to test that assumption, but ORC defaults to a 64 megabyte stripe, and Parquet goes to 128 by default. And so you can see that the rows per stripe, ORC got 18,000 and Parquet got 88 because of the details. So I suspect that the compression would be better if, and the read performance better if we made those numbers bigger for such a big table. All right, now column projection. Column projection is one of those things that happens all the time. It's often the case that out of those 100 columns in your table, you only need a few of them. And so there are some of the benchmarks that go through here. I just put the zlib for the 3 for ORC and Parquet. Obviously, Avro, the numbers are going to look exactly the same. For JSON, the numbers are going to be exactly the same because they're row major. So if you just need 2 of the columns, you are not going to see any difference. It's going to have to read everything. For ORC and Parquet, they actually read a lot less bytes. And so you can see that the percentages of time spent reading the first 2 columns in each of the different formats is much, much less. So it reads a lot less data and runs much, much faster because it just reads the bytes you need to look at. All right, now, I really need a benchmark for predicate pushdown. Predicate pushdown is where you push a filter condition down into the reader. That has a huge impact because often you can throw a lot of data that never has to be decompressed, and so you can skip right over it. There are 2 cases where it happens a lot. The case where you have a very selective filter or where you've sorted data. For example, I've talked to customers that want the partition based on country and then by product, and so they end up with these little tiny partitions because really, does Estonia have very many instances of each of your product? Probably not. So they would be much better off by sorting the data and putting them into the same file and then using predicate pushdown to say, okay, we just don't skip over the sections of the file that have the wrong countries. That lets you keep large partitions, which makes Hive perform much better, and it lets you still skip over the data without actually reading it. So that does a lot of good things. ORC has also added bloom filters, so you can say, I need a bloom filter on this column. That's very useful for things, let's say your sales table where you have to sort it based on time because that's the way you normally query it, but every once in a while you need to look for users. And so if you're looking for this list of 10 users and you want to find all their transactions, if you create a bloom filter, then it can take that list of 10 users, see if this file has any of those 10 users in it potentially, and then pass it back up. the final use case that helps a lot, actually, is that ORC and Parquet store metadata. I didn't bother benchmarking this because it runs so fast it's not actually that useful. And you store in the file footer the file schema, the number of records, and the min, max, and count of each column. Now, this actually lets you do a lot of things. For example, looking at the taxi data, I was looking for different facts about it, and I could easily see that the drop-off time had incorrect values because there was the minimum value for the drop-off time was from 1970. Probably not a good value. So it lets you look at that kind of analysis quickly. Furthermore, you can answer a bunch of questions very quickly because of number of records and this file schema. Okay, the biggest thing I want to point out is that everything changes, right? Especially as part of this, we're going to start changing the file formats. So this presentation is very much a point in time. And on the other hand, for complex tables with lots of common strings, right now your best choice is Avro, as long as you don't need projection, right? If you need column projection, then you should do other things. But if you just want small, fast access to data and you're willing to read it all for every query, then you should go with Avro. For the other tables, ORC did really well. Actually, we've got a performance guy named Gopal that does an amazing job working on ORC, and he's done really well with it, obviously. And the final thing is, I would strongly encourage you, okay, so the benchmarks have run on one set of hardware, and they're very, very young, right? They're a pull request on ORC right now, and so give us a week, and I'd love for you guys to pull it down, try running it on your hardware. If you've got other open source data sets, I'd love to have people contribute plugins to work on it, because making these file formats better helps all of us, right? And the better that the test data sets are, and the more public data sets we have, the better our data formats will be. Now, there's also some fun stuff. We built an open source benchmark, which is available as the pull request. It'll go into the ORC mainline soon. We've got most of the pieces to convert data files back and forth, which is actually kind of handy, right? It's kind of handy being able to take this JSON document, give it a schema, or have it figure out the schema and convert it into ORC or Parquet. Converting ORC and our Parquet back and forth. Most of the pieces are there. We haven't done the glue to hang them together. And finally, there's a randomized parameterized generator that you can give a table definition to, and it'll generate the data for you. Thank you. So that's what I had. Are there any questions? Yes.
Yeah, I thought you mentioned at one point you said. I thought you mentioned at one point you said you actually did the benchmarking on a single host. Is that correct?
Yeah, I used a single host because they're mostly micro benchmarks.
Sure. And then so, what would networking bring into this? I mean, my experience says that you can gzip, send it over the wire, and uncompress faster than you can send an uncompressed file.
It depends on your networking, basically. But obviously, part of what I was trying to pull apart was separate off the cost of how much data I was reading. So actually, the benchmarks tell you how many read requests there are, how much data got transferred. And so you can start to fill that into your calculations. Actually, he's saying in a MapReduce context, you get a little bit different results. And actually, we're working on, a different team is working on some benchmarks that look at that more directly from the, how fast is it to read local data versus remote on HDFS versus on disk. Okay, I think I'm getting kicked out at this point.
Unfortunately, our time is up.
So thank you very much. I'll be around to answer questions.